Today, I'm happy to have Newmark from MIT talk about the Coherent CAPTAIN-Mills experiment. Anyway.
Thank you. Yeah, thank you for inviting me here today, and thank you for the introduction. My name is Darcy Newmark, and I'm a grad student at MIT. And today I will be talking about the Coherent CAPTAIN-Mills experiment, CCM. This is a picture of inside of our detector. We're a 10-ton liquid argon detector located at Los Alamos National Lab. And we're entirely light collection, both scintillation and train-coupled light, as you'll see. And we're studying neutrino and BSM physics. So we're going to go over a couple anomalies in the experimental neutrino sector. And those will motivate the need for experiments like CCM. And we'll discuss the specific how CCM works. And then we'll talk about our program to identify train-coupled light on an event-by-event basis. And finally, we'll close on how that feeds into our physics program. Okay, so let's start with a couple case studies. We're going to start with LS&D in the 1990s. So LS&D was also at Los Alamos National Lab. So the same 800 MeV proton beam, though things are a bit different nowadays. So they had an 800 MeV proton beam with a rather wide beam spill of a few microseconds. And it impinged on a water and high Z target. And that produces a large flux of electrons, positrons, photons, as well as pions from the hadronic decays. And the majority of pi minuses will capture on nuclei in the target, while the pi pluses are free to decay at rest. And so the pi pluses have a very short lifetime of about 20 nanoseconds, and they produce this monoenergetic 30 MeV neutrino flux pretty quick in time with the beam because of that short lifetime. And then also from this pi plus decay, you get mu pluses, and the mu pluses have the four-body decay, producing other fluxes of neutrinos, of nu e's and nu mu bars, with these energy fluxes that are brought from the four-body decay. And at a longer time constant, so a 2 time, so these are delayed fluxes of neutrinos. So LS&D was originally designed to study neutrino oscillations, so to study electron anti-neutrino appearance. So from this flux of nu mu bars, they can oscillate producing into nu e bars, and then they're studying the inverse beta decay interactions. And so LS&D was at an L over E, so the distance the neutrinos travel over the energy they're at of 1, which is important. That's what governs this neutrino oscillation phenomenon, where you have the neutrino mass eigenstates traveling at different speeds. And then when you measure, you see different flavor eigenstates based on how far the neutrinos traveled. And so the detector, here's a diagram of the detector. It's also a light collection detector. It was 167 tons of liquid scintillator that was lightly doped, allowing for both the Trenkov and scintillation light identification. It was instrumented with about 1,200 PMTs for 25. And so their primary signal that they were measuring was this inverse beta decay interaction. So of the electron anti-neutrinos interact with a proton, giving you a positron and a neutron. The positron gives you a prompt flash of Trenkov light, a cone, and then you have the scintillation light as well, and prompt signals. And then I think a few microseconds later, the neutron will capture, giving you about an MeV signal. And so it's a threefold coincidence measurement, so it's pretty robust to random background. Okay, so what did LS&D see? This is their our final results of L over E versus counts after subtracting off their pre-beam backgrounds. And so they saw an excess of about 90 events over some of their expected backgrounds. They have a couple here from the pi minus to pi minuses. When they don't capture the you get a mu bars. And then also from mu minus, so from that same pi minus decay, you can get mu minus, and also cosmic muons can introduce mu bars as a background. And so, yeah, so they saw an excess, and this was has been thought of in terms of scaling neutrinos. And so the follow-up to LS&D. So MiniBooNE is has the same L over E, but very different systematic. So in 2010s, MiniBooNE was built using Fermilab's booster neutrino beam, where they have an 8-JeV proton beam hitting a beryllium target. And then again, you get these flux of hadrons, ions and pions. And then through their magnetic focusing horn, they can either select pi pluses or pi minuses to run a neutrino or anti-neutrino mode. And then you get the same decay neutrino products that LS&D was seeing, but at different energies. So these energies peaked around 500 MeV, and they were closer to 500 meters away from the source, giving them the same L/E of 1. And MiniBooNE was also similar in that they collected light, but this time it was all mineral oil, and it was a much larger detector of 800 tons with 1,500 PMTs. And they were reconstructing only Cherenkov light from the charge current quasi-elastic scattering of the NUEs that they were studying, or NUE bars, depending which mode they ran. So what MiniBooNE saw was very interesting. So this is their final reconstructed energy versus events, and they have this characteristic low energy excess. It's electromagnetic-like, as well as the cosine theta of these events, and you can see it's a high cosine theta. And so this signal is very difficult to fit. You actually can't get a just 3+1. And so, yeah, so this anomaly has been pretty long standing. This is almost. Yeah, and then we're going to talk about one more experimental anomaly that's a completely different source of neutrinos. So now we're thinking about neutrinos from radioactive decays at the BEST experiment. So to start a little history, SAGE and GALEX were solar neutrino experiments that ran 80s and 90s, I think, studying the low energy part of the solar neutrino spectrum. So most solar neutrinos are below 1 MeV, which means if you want to study them, you have to have a target nuclei that has a very low Q value, and gallium satisfies that. It's like 230 keV Q value. And so what they were measuring was NUE capture in the gallium and then produce germanium, and then they count these germanium daughters. And so aside from the solar neutrino measurement, SAGE and GALEX put calibration sources in their detector of chromium-51 as well as argon-37, which electron capture, giving you a low energy electron neutrino that they can measure. And using these known sources, they saw a deficit of germanium daughters. So BEST is a follow-up in the 2020s. You study this apparent mismatch in what we expect of the gallium neutrino capture cross sections. And they were using a very intense source of 3 megacuries, and they have this inner and outer target design. So you have an intense source in the middle, and then they basically had an exposure period where they allowed this neutrino capture interaction to happen, and then they count the germanium daughters at the end within the inner and the outer target. Yeah, so what did they see? So in the middle plot here, this is the for the inner target. So blue is predicted and red is measured, and this is outer target predicted and measured. You can see at both of these targets, they see about the same 20% deficit of germanium daughters that they would expect from their source. And so this does bring the gallium anomaly to 5 sigma. And there have been many theories about perhaps maybe we just don't understand what's happening in gallium since then. And there's been a lot of work to do that, to look into that. And it seems like, to the best of our knowledge, this gallium anomaly isn't caused by mismodeling of nuclear physics. It seems like there's something else going on. So yeah, so what these experiments have in common is that you can think of them in terms of sterile neutrinos. So I mentioned we have our 3 mass eigenstates. But if you introduce a 4th mass eigenstate that participates in the neutrino oscillations, but not in the weak interactions, because the neutrino flavors are very constrained by the width of the Z decay. So that's why a sterile neutrino would only participate in oscillations and not weak physics. That could explain either an appearance or disappearance of whatever flavor you expected to measure. Okay, but it's not just 3 experiments. There's really many experiments. Here's a non-exhaustive list at the bottom of all the experiments that go into these global fits. So, what global fits are is taking all of the experimental data and trying to fit for one sterile neutrino mass eigenstate. And so, but the issue is there's a lot of tension in these global fits. So this plot, the x-axis is our sine squared 2 theta of our mixing angle. So the yellow here is electron disappearance, the purple is muon disappearance, and the green is electron appearance, which correspond to different sets of experiments. And so the fact that these different color regions have different domains on the x-axis is fine. That's totally expected because you expect different mixing. But the issue is in the y-axis. So the y-axis are delta m squared from the first to the fourth mass eigenstates. And so since these experiments do not overlap preferring the same delta m squared, that's really a problem. You can't have multiple delta m squared for the same sterile neutrino. Yeah, so of course there's been looking into like 3 + 2, 3 + 1 + decay, and so on, but none of these models so far have been able to adequately explain all of the experimental anomalies and data that we've seen in neutrino physics. And so that motivates towards looking to the dark sector. Yeah, so these experiments are ultra large, measuring these very weak decays of neutrino interactions. So it would make sense if there's dark sector physics also happening, being dark sector particles being produced in your beam dump, you would also be measuring that in your detector because they're very sensitive. And so possible dark sector solutions are neutrinos coupling to dark sector mediators. You could have mixing of the neutrino states, or you could be making dark sector particles and measuring that and not your neutrino interactions that you're studying. Okay, so this is a very broad case, as I'm sure everyone here knows. And so this means experimentally, if we want to be able to test this, we need experiments that are very like nimble, very agile. They don't cost a lot. They can cover a lot of different parameter space, and they're quick. An example is the experiment I work on, CCM. Okay, so let's start with the timeline. So CCM is about the same age as a grad student. It was developed in 2019. Our prototype detector was called CCM 120, which was built and instrumented with 120 8-inch PMTs as a test bed for SBND. They're now currently installed and running in SBND. And this engineering run of about 6 months of data did produce physics results, which we'll talk about at the end, published in the middle of 2022. So then a few years later, over COVID, we upgraded our instrumentation from 120 8-inch PMTs to 200 8-inch PMTs, as well as increasing our veto PMT coverage. We have 41-inch veto PMTs. We have an optically isolated veto region, and increasing the shielding around our detector. And we took engineering data in 2021. And currently, we're in the physics run era of 2022 to 2025, a funded 3-year data collection, where we've improved our DAC to handle more data streams, higher rates of data. We've installed additional shielding around our detector, and we're looking into calibration using Michel electrons from cosmic muon decay, so that instead of just having a few MeV source calibration, we have up to 50 MeV calibration. Okay, so we are at Los Alamos Neutron Science Center. So we have this 800 MeV pulsed proton beam here, similar to LSND, but this beam is pulsed at 20 hertz, 100 microamp current, and it's a pretty short beam spill of 290 nanosecond at the base. It's a triangle shape because of how the protons are fed into the proton storage ring. They go around and stack them up until you get a triangle. So at the widest point, it's about 300 nanoseconds, but the full width half max is around 145 nanoseconds. And so this proton beam, again, hits a target. We have a tungsten target, and this produces fluxes of electrons, positrons, photons, as well as pions from the hadronic decays. And so the pi minuses, again, the majority capture, while the pi pluses will decay, giving you a prompt monoenergetic muon neutrino flux at 30 MeV. And then you have these delayed NUI and MeV bar fluxes from the mu plus decay. And so our detector is 23 meters away from the target. So we get about 10 to the 5 neutrinos per centimeter squared per second out our detector of all 3 flavors. Each flavor individually is 5 times 10 to the 5 flux. And we are at an above ground facility, which means the short beam spill window is really crucial to reduce our steady state sort of cosmic backgrounds, primarily cosmic ray backgrounds. So LSND had many microsecond beam spill window, while ours is around 300 nanoseconds. So we can reduce our rate of cosmic backgrounds by around an order of magnitude or so. Okay, so the Wuhan facility, to put this into perspective. So here is the Wuhan facility. This is power produced facility versus background rejection. And background rejection here is a proxy for your beam spill window, because as I mentioned, reducing the beam spill reduces your backgrounds essentially for your random backgrounds. So the Wuhan facility is not the most powerful facility, but it does pretty well in terms of background rejection through a short beam spill window. Put into context, this is PMT at Fermilab, some of the PIPs at Fermilab, JPark, SNS. And currently there's, I think it's a CD0 upgrade plan in the next 10 years to increase our background rejection by an order of magnitude from reducing our beam split window down to 30 nanoseconds. And they'll also be increasing the power by a factor of about 2. So we'll move here up to this star. So a pretty competitive facility if you care about signal to background. And so you can make up for the lack of power with a bigger detector. Okay. So here is CCM at Wuhan. So the proton beam comes in parallel to the ground and then it bends 90 degrees and it hits our tungsten target from the top down. And then we're 23 meters away radially from this target located here in the Wuhan facility. This is a picture of our inner array of 208-inch PMTs being lowered down into the cryostat. So within this array of 208-inch PMTs, we have 7-ton active volume of liquid argon. And then outside of this, there's an optically isolated veto region, which has 3 tons of liquid argon. It's a hermetic veto instrumented with 41-inch PMTs. And so in our current ongoing 3-year physics run cycle, we're expected to get about 1.5 times 10 to the 22 protons on target. Here's another picture of the inside of our detector. So what you'll notice here, so these circles are our PMTs. But some of them are shiny and some of them are dull. That's because the PMTs that look like they have a matte finish here, they are coated in tetraphenyl butadiene, which wavelength shifts the liquid argon scintillation light from the UV into the visible so that our tubes can record it. And then the walls of our detector here, they are also coated in, or I guess covered in TPB coated foils. And our timing resolution is governed by our digitization time period. So we digitize every 2 nanoseconds. So yeah, you can fit for maybe around 1 nanosecond timing resolution, but 2 nanoseconds is definitely a good metric for our timing resolution. And so we have liquid argon, which is a prolific scintillator. So we have a very wide energy detection range from about 100 keV, which helps us measure coherent nuclear recoil signals, up to 200 MeV to measure high energy electromagnetic type signals. Okay, so let's talk about our backgrounds. So we are 90 degrees off axis from the proton beam. So we're only measuring decay at rest products, so we don't have to worry about decay in flight contamination. So our primary backgrounds that are in time with the beam and that we can't measure before, because we take about 8 microseconds of data before the beam trigger to measure our steady state backgrounds, but the in-time backgrounds are the fast neutrons. And so we have basically 2 handles on the fast neutrons. One is through shielding. So here's our 800 MeV proton beam going down, hitting the tungsten target. There's 2 tungsten targets here in this configuration. And then that produces your speed of light, weakly interacting particles, basically speed of light, neutrinos, ALPs, whatever dark matter candidate you want to study. So those are going to be produced in the target and travel basically unimpeded to our detector where hopefully they interact and we can measure them. But the neutrons that are produced in the target will be attenuated by the shielding. We have a couple meters each of steel, concrete, lead, and some borated poly between the target and our detector. So the neutrons take this sort of random walk to our detector, so increasing the propagation time as well as attenuating the neutron flux and the neutron energies. So that's one method, is shielding. The other method is through timing. So on the left-hand side here, you'll see this green arrow. So we have what we call our gamma flash measurement. So we have an EJ detector, which is a scintillator coupled to 1 PMT, and there's no shielding. Well, there's a pinhole without any shielding between this EJ detector and the target, which means we can measure this prompt flux of gammas produced at the target. So we get basically a pinpoint for when we expect speed of light particles at CCM. So here's an example of data from this EJ detector. So you can see single gammas, and then you see like a wall of neutrons. So we use our single gamma times to basically get a T naught for our region of interest. So as I mentioned, we have a triangle beam shape, so you can see that here. So this is a time profile. These dashed lines and gray dash is what the neutrinos and dark matter potential candidates would be produced like in time, while this solid black line is the neutrons without any shielding, but the red is our neutrons that we measure at CCM after all of the shielding and attenuation. So we use this gamma flash measurement to get a start time for our ROI, and then we use measurements of the neutron wall to get an end time so that we can have a clean slice of data where we don't expect there to be any neutron contaminations. Okay, so let's talk about how we get light in the liquid argon. So when you have argon atoms here, you need a charged particle to travel through the argon and either excite or ionize the argon atoms. Both pathways end up to an excited argon dimer. So it's actually two argons in a bound state with an electron orbiting. And then this bound state has two different spin configurations, a singlet and a triplet spin configurations, which have different decay time constants. And so this excited state, when it decays, it produces the scintillation light. And so liquid argon is a very prolific scintillator, producing about 40,000 photons per MeV. The scintillation light is produced isotropically, and it has a fast component from the singlet configuration, which is measured between 5 to 8 nanoseconds. And it has a slow component from the triplet spin configuration, which is around 1 to 2 microseconds. In the wavelength, so it's produced almost entirely in the UV, pretty narrowly peaked around 128 nanometers. Okay, but then we also get Cherenkov light. So the way you make Cherenkov light in any polarizable medium is you have a particle moving fast enough with a velocity greater than c/n through the medium, and then it forms these little dipole moments. And then as these atoms relax back into their ground state, they release this coherent wave of photons at a characteristic angle, theta c, which is related to the velocity and the index of refraction of light in that medium. And so Cherenkov light is a lot dimmer than scintillation, only about 700 photons per MeV, but it is directional, which is very useful if you want to cut out backgrounds. The Cherenkov light points back to the particle direction, and it's incredibly prompt. It's about like picosecond start time, whereas the scintillation light is more on the order of nanoseconds. And it's produced broad spectrum. So the intensity as a function of wavelength falls off as 1 over lambda squared. So the majority of Cherenkov photons are in the UV, but they do extend out into the visible region. Okay, so let's talk about how we collect light at CCM. So as I mentioned, we have these coded and uncoded PMTs. So the coded have the TPB wavelength shifter on them. So if a UV photon hits the TPB coding, it can be wavelength shifted, and then about 50% of the time, it's re-emitted directly into the PMT. And this is what we call our direct wavelength shifted scintillation light here. And so in our coded tubes, the difference between our early Cherenkov light and our direct wavelength shifted scintillation light is very small. It's really based on the production time constants between scintillation and Cherenkov light, which is nanosecond to picosecond. So it's a their signals are pretty close together in time. But if we consider our uncoded PMTs, so our uncoded tubes are only going to be sensitive to the visible light. So they can observe the broad spectrum, the visible portion of the Cherenkov light, as well as wavelength shifted UV scintillation light. So immediately the first photons that will be registered on an uncoded tube, if there's Cherenkov light in an event, is going to be this visible portion of the Cherenkov light. And then you get a wider time delay between the Cherenkov light and the delayed wavelength shifted scintillation light because of the TPB time constant, which is around a nanosecond, as well as propagation light has to go from TPB into the PMT. Yeah, so we use a combination of our 2 nanosecond timing reckoning, which is fast enough to separate out this early visible portion of the Cherenkov light and the uncoded tubes from the wavelength shifted scintillation light. Okay, so yeah, so let's talk more about how we're identifying Cherenkov light. Okay, so let's get into why we want to do it. So of course, trunk of light is only produced by charged particles, so it does give you some handle on particle discrimination if it's charged or neutral. It also gives you a handle on the threshold effect. So we're not measuring the Cherenkov cone to measure velocity. We're really just seeing if a particle has produced Cherenkov light, because then it means it's a charged particle moving fast enough, so it's not a slow proton or a slow alpha producing Cherenkov light in our detector. Yeah, and so for these experiments like Super Conde that are specifically measuring Cherenkov light only, and MiniBooNE as well, they can use this sort of ring topology to do even more discrimination between particle types. So you have your through-going muons, which don't multiple scatter, which are pretty clean circles, whereas your electrons will multiple scatter, fuzzing out this Cherenkov ring. And so yeah, so really the best of all worlds would be if we can measure both Cherenkov light and scintillation, because Cherenkov light gives you directional information as well as particle discrimination. And scintillation light, if you have a prolific scintillator, you get a lower energy threshold as well as better energy resolution. So you can really increase your physics program if you're able to cover a wider range of energies with better accuracy, essentially, as well as powerful background rejection through the particle discrimination and the pointing. Okay, so there's basically two ways to do this experimentally. The first way is what Alice and Dee did. It's the easiest way. It's reducing your scintillation light. So they lightly doped their scintillator so that they can tune the amount of scintillation to Cherenkov light, so it's easier to pick out the Cherenkov photons. So this is easy experimentally, but one drawback is that since you're getting less scintillation light, you get worse energy resolution and a higher energy threshold. The other experimental way to do it is to be smarter about how you're collecting your light. There are really two differences between scintillation and Cherenkov light that you can exploit. The first is the difference in the time spectrum. So experiments like EOS and NuDOT are trying to instrument like slower scintillators so that they can increase the time delay between Cherenkov and scintillation light, so it's easier to pick out the scintillation photons. The second way, which is what CCM primarily uses, is difference in the wavelength spectrum. So we use our combination of coated tubes, which can see basically all photons once they're wavelength shifted, and uncoated tubes, which can only see visible photons, to try to pick out different mechanisms of light production. But this is difficult, and it's an ongoing problem, I guess. Okay, so what are we doing? So it's pretty easy. It's basically 3 steps. We use a well-known source of both scintillation and Cherenkov light that we calibrate, an optical model in JANT4, and then we conversion and comparative data. What we're using is a sodium-22 source. So sodium-22 has 2 different decay pathways, 2 primary decay pathways. The first being beta plus decay, so it emits a pretty low energy beta plus, and then it's in an excited state of neon, which de-excites, giving you a 1275 gamma. And the second pathway is when sodium, about 10% of the time, sodium-22 directly decays to this excited state of neon, which de-excites, giving you that 1275 gamma. And our sodium source pellet is encased in stainless steel. So this beta plus particle annihilates pretty much instantly, giving you 2 back-to-back 511 photons. And we don't expect any Cherenkov light from the beta plus because it's in that stainless steel capsule. But we do expect Cherenkov light from the 1275 gamma. The threshold for electrons making Cherenkov light is about 300 keV. So when this 1275 Compton scatters, typically it deposits about 2/3 of its energy into an electron, so you get order MeV or less electrons that produce Cherenkov light. And so, yes, and then we simulate this decay in our detector in JANT4 and calibrate an optical model and including fitting for the scintillation light parameters, which I'll talk about today. And then finally, we can compare simulation to data and see if we're able to pick out the Cherenkov light. Okay, so here is an example of some of the data from our sodium calibration source. So this pink is a histogram of charge in the first 90 nanoseconds of our event. So it's a proxy for energy produced from our sodium decays. Our sodium calibration source is at XY of 0, the origin of our detector, and then we move at different Z's. So Z of 0 is directly in the middle of our detector, and then we move it up and down closer to the top and bottom faces of our detector. But this is the energy histogram for sodium at the center. And so we experience inequality cuts and select events and sum the charge in the first 90 nanoseconds and compare that to what we call the blank source. So it's the same source calibration rod inserted in the detector, but there's no source pellet to measure our background spectrum, essentially. And so you can see there are two different peaks on top of the background spectrum, and these are scaled to be the same number of triggers. And so this lower energy peak corresponds to the electron capture decay pathway, and this higher energy peak is the beta plus decay. And so we select events in this high energy peak of the beta plus and accumulate the pulse series on each PMT to compare to simulation of the same beta plus high energy beta plus decays. Okay, so then once we're comparing JNOT4 simulation to data, we fit for some parameters of our optical model as well as our light parameters. So in JNOT4, if you've ever simulated something that produces a lot of optical photons, it is very slow. So what we do is we simulate without any scintillation time constants, essentially instantaneous light production. And then we accumulate many events and convolve these, what we call the yields, the photon arrival times without any time constants. We convolve them with our scintillation time profile, and then use gradient-based minimization to fit for our time constants. And we're fitting this effective likelihood, minimizing this effective likelihood, which is good for these sort of stochastic Monte Carlo methods, and in the high stats limit, it approaches a Poisson distribution. So here's an example. So this is on a single PMT. We fit all tubes. We're fitting about 500 time bins, so up to 1,000, 2 nanoseconds each, for across our different data sets. And so the gray is our data, and then the pink is our simulation, and we're fitting from 6 nanoseconds to 1 microsecond. This is going to be important that we're not fitting the early time region, we're just fitting the late time region, because we don't want to have to worry about the Cherenkov light skewing anything in our fit for the scintillation parameters. And so what we fit for preliminarily is a ratio of singlet to triplet light of about 0.3, a singlet time constant of about 6 nanoseconds, and a triplet constant about 740 seconds. And the reason this is a bit lower than what I said of 1 to 2 microseconds is because we do not filter our liquid argon. So we do have contamination in our liquid argon that essentially breaks up the triplet state before it can reducing the lifetime, as well as this ratio singlet to triplet. If you read other literature values, they find things closer to 0.2 for electromagnetic particles. So we are getting closer to 0.3 because our triplet states are being eaten up by contaminants, essentially.
Excuse me, why the data is oscillation?
Yeah, so these are this is the triplet region. These are very low energy events. So even though we've accumulated about 50,000 events in data, it's this is the expected average charge. You can see it's less than the -2. So it's just very low energy events. If we calibrate using higher energy events, it would probably be smoother. Okay, so now let's compare data to simulation. So if you remember this little toy diagram of what we expect on our coated tubes of the Cherenkov and scintillation to pretty much be butting up right against each other. And on our uncoated tubes, more of a gap between the time of the Cherenkov and scintillation. So this is our accumulated events on one PMT that is coded, and the black is data. The blue is simulation with Cherenkov light, and the pink is simulation without Cherenkov light. And so now we're going to zoom in on this early region. So you can see there's small differences between the blue and the pink. So that's because the time constants are pretty close. So if we only had coated tubes, yes, we might be able to see that we're seeing Cherenkov light, but it's not obvious. But now if we look at the uncoated tubes, it's clear, it's a few orders of magnitude that the Cherenkov light has contributions in the 0 to -10 nanosecond region of our event start time, where the scintillation only simulation does not. So this is the first observation of Cherenkov light in liquid argon sub-MeV particle. The only other observation of Cherenkov light in liquid argon, to my knowledge, is from Icarus, and they used cosmic muons, which are much higher. So this is really leaps and bounds above that since we're using sub-MeV. Okay, so now let's look at a couple pre-event metrics. So based on the previous plots, we expect trend couple light most distinct from scintillation from this -10 0 of our event start time. So we can count the number of hits on our uncoded PMTs in this -10 0 early region and compare data to simulation. So this is number of tubes with early hits, and this is only for uncoded tubes, number of events. So this green solid is the Monte Carlo, the simulation, if we were only simulating scintillation light. This green dashed is Monte Carlo with simulation and trend couple light, and the blue is data with statistical error bars in each bin. So you can see the data. We're still looking into tuning the trend couple light, like the mid UV absorption in our detector. So that could be causing some of this difference in data and simulation. But it's clear that our data definitely agrees better of simulation with scintillation and trend couple light. And in about half of all our events, we do have hits in this early time region. So we're expecting to identify trend couple light in about half of our sodium events. Another metric is using simulation, using our truth level energy of our highest energy beta produced in the decays versus the number of Cherenkov photons detected on the uncoded tubes. So you can see that most of the events are produced, or Cherenkov photons are produced from about 1 MeV electrons, but we can get down to close to 1/2 MeV electrons, identifying Cherenkov light. So I'm going to show you some event displays. So these are produced from simulation. So these are two different events. This is our detector unwrapped. The dashed lines represent our uncoded tubes, which is about 20% of all tubes. And this up on the right here is our summed waveform across all tubes. So the gray is the data, and then the green is just highlighting this early time region, the -10 0. And we're plotting the total charge in all tubes in this -10 0 region. You can see these are 3 uncoded tubes, which see early hits of around a PE or so each. And they are spatially correlated, which you expect from trend couple light. And then here's another example of a different event where you can see Cherenkov ring basically around the sides of the detector here. And so this is simulation. So we know that this is entirely produced. These photons are entirely produced from trend couple light. There's no scintillation contamination. Now let's look at data. These are two different events in data. And so you can see, again, we're going to look at the early time region of -10 0. We see that same sort of pattern of these 3 tubes, as well as these 3 tubes being lit up. So this is very promising that we are seeing trend couple light on event by event basis around 1 MeV particles. And the full statistical analysis is still ongoing. Yes, so what else is ongoing? We're redoing our event reconstruction using GraphNet, which is a graph neural network used by neutrino telescopes like IceCube. And we're going to start with reconstructing the vertex and energy of our events, and then move on to reconstructing direction, as well as trend couple light. Those two will go hand in hand. Yes, and then we have a cosmic muon trigger. So on top of our detector, we installed small scintillator detectors. So 2 5 by 5 by 1 centimeter scintillator squares, and we trigger on coincidence going through 2 scintillator squares. So we can trigger on cosmic muons, and then this gives us a nice sample of Michel electron produced in our detector from the muon decay, which, since they have a well-known energy spectrum, we can calibrate up to higher energies. And then we also have data from an off-axis source calibration. So I mentioned that the one we've currently used is at 0 0, and then the Z changes, but this off-axis has an extension arm. So, and we can rotate it around, so we can test many different XY positions as well as different Z positions. So that should hopefully improve our data reconstruction as well. Okay, so now let's connect it back to the physics program and what we're trying to do at CCM. So, okay, as a reminder, 3+1 isn't very satisfying given all the experiments we have. So this motivates looking towards a dark sector for a solution. And so we need experiments like CCM that are quick, cheap, and can cover a lot of different models through really taking advantage of all the information available in liquid argon. through both Cherenkov and scintillation light. And so first, let's think about the final state signal. There's basically two classes of final state signals that we're looking for in our physics searches. One is electromagnetic, so electrons or photons in the order of MeV range. And these will produce both scintillation and Cherenkov light. And the primary in time background that we can't measure out, essentially measure and subtract off, are these fast neutrons, which will only be using scintillation. So in a single event, if you can identify Cherenkov light, that's a very good handle that we know it's not a neutron background. And then our second class of final state signals are lower energy nuclear recoils of order 100 keV. And these will produce only scintillation light, but not Cherenkov light. And for these, our primary background are low energy radioactive beta decays, so mostly argon 39, which will produce scintillation and Cherenkov light. And given what we've seen with our sodium source, we're expected to be able to pick out the Cherenkov light even from low energy beta decays like these. Yeah. Okay, so let's talk about a couple models. So first, we're going to talk about the dark sector coupling to meson decays as an explanation to the MiniBooNE anomaly. So a lot of people here worked on this model. So the MiniBooNE excess, what's important about it is that it was only in target mode, which means it really corresponds to production of hadrons, of pions and kaons. So you could think about the electromagnetic excess in MiniBooNE being caused by photons and not electrons. And so these excess of photons could be produced when you have dark matter particles coupling to your pi pluses and pi minuses. And so, yeah, and then in the detector, they'll decay producing photons. And so this here is couplings and the MiniBooNE allowed region in the blue here. MicroBooNE limits are excluded upwards of this purple line. And then CCM are these two different red lines. So this is CCM's expected sensitivity for CCM 200. So the red line is with our current background estimates. The solid red line, that is with our current background estimates. We're expected to say something about stuff to the right of this line. And then this dashed line is our background free limit, which is essentially where we get with Cherenkov light. And so that increases our sensitivity by a couple orders or times two about through identifying Cherenkov light. Okay, the next model I'll talk about is axion-like particles in the QCD axion. So this is the standard mass of the axion versus coupling. And so CCM 120, well, let me start with, we expect axion production, axions coupling to the intense fluxes of electrons, photons produced in the target. And then the axions can be detected in our detector through production of these electromagnetic final state signatures. And so CCM 120's limits are these batched black horizontal lines here in this beam dump region. And CCM 200's expected sensitivity is the blue line. So the blue dashed line here, you see it's CCM 200's expected sensitivity without Cherenkov light, but then with Cherenkov light, we get down to this lower region of here covering the majority of the cosmological triangle, which is unprobed by these terrestrial experiments, probing or looking sensitive to around 1 MeV mega electron volts axions. And so with Cherenkov light, we're really able to reduce or increase our sensitivity by orders of magnitude because for these sorts of processes, these are forward going scatters. And so with the directional reconstruction, that's really powerful in rejecting backgrounds. Okay, and then another model I'll talk about is left-focused dark matter, and theory work done here. So we're most sensitive towards these like 10 MeV mediators. So you can consider pi knots produced in the target, and when they decay, giving you 2 photons. This photon can have coupling to a dark matter particle, which then coherently scatters in our detector. And so CCM 120 in just the 6 months of engineering run data was able to carve out this blue region of parameter space here. And CCM 200 is expected to do many orders of magnitude better here through longer exposure time. Yeah. And then finally, the last model that we're thinking about is heavy neutral leptons. So if we consider this prompt monoenergetic flux of 30 neutrinos, then you can have a non-standard dipole portal interaction where they upscatter into H and Ls, and then the H and Ls decay and emit a photon within our detector. And so this model is very nice because this upscattering process gets a, I believe it's Z-squared enhancement in the cross section. So our many meters of shielding between the target and CCM is very helpful in increasing our expected production. And then our final state is around a 10 MeV photon. So here, this is one potential solution to the MiniBooNE anomaly. This is a MiniBooNE allowed region in pink here. And so you can see other experiments have explored the right-hand side of the parameter space, but the left-hand side here is unexplored, and that's where CCM is most sensitive to. And so we're able to probe H&L masses up to about 30 MeV because we have 30 MeV neutrinos, and then these dipole coupling constants here. And so these two different lines in the blue, so this top line is if we cannot identify triangulate with our expected backgrounds, and then this bottom line is our, as we approach the background free case where we can identify a twinkle light on identified cases. So you can see we do gain a lot in sensitivity with this. Okay, and then additional physics searches. There's recently published looking into the X17 atomic key particle in CCM. So considering events produced in the glass of our PMT and the oxygen atoms in the glass. As well as we're looking into thinking about a magnetic moment using just this prompt flux of muon neutrinos. And the final state is a very forward-going scattering. So Cherenkov light would be very nice for rejecting a lot of those backgrounds. And then finally, we are working on a measurement of our charge current newly argon cross-section, which is going to be very relevant to DUNE and supernova physics. Yeah, so to summarize, there's a lot of anomalies in the field that can't be explained by 3+1. And so this motivates looking towards the dark sector to probe, to try to find explanations for these experimental anomalies. And CCM is a prime example of a agile, sort of fast, broad experiment that can probe a broad range of parameter space. Because partially because of the location, so located at the Lujan Center, we have really intense fluxes of our pions, electrons, photons, as well as neutrinos. And so we can study dark sector coupling to those particles. And then because we're using liquid argon, we have a very wide energy detection range. So from 100 keV nuclear recoils up to 200 MeV electromagnetic particles. And furthermore, because of our reconstruction techniques, we can really leverage the Cherenkov light to basically get to the background free case in a lot of searches. Okay, so thank you for listening, and thank you to our collaboration.
Any questions for Darcy?
You read, I think it was 47, your leptophobic dark matter. Yeah. So in all the other models, when you compared CCM 120 to CCM 200, it was like a modest improvement.
Yeah.
What's driving this dramatic improvement here?
A lot more data.
Okay.
Yeah, so this is mainly limited.
Got it. It's really impressive.
Yeah, towards them. Any other questions? Can you show the picture of the Cherenkov rings? I just want to get an idea or get an understanding of from super. I think it was from Super K.
Yes.
Just out of curiosity, can you tell us about the difference in the colors and how that might also affect sort of like in the pictures?
I don't know what these colors represent. I would imagine they have something to do with timing or photons detected. I don't think are you thinking they're correlated to wave?
I wasn't sure.
I don't know. I don't think so. I wouldn't expect it to be like that.
Okay. And then, do you have any estimates for the calculation of the charge current neutrino liquid argon cross section?
Yeah, we're expecting, I think it's, I can give you the slides, but I think it's around 1,000 events we're expecting, maybe with a 30% uncertainty on our cross section measurement.
Okay. And is that uncertainty across the entire energy spectrum?
Yes, it should be.
And then I guess I don't know if you showed this, but do you have the energy resolution as a function of the measured energy?
Not at the moment. We're still working on that. Yeah, we've grouped our a lot, you know, different reasons, everything.
I have two questions. First is you show that MiniBooNE and BEST have some phenomena. Maybe there is a nuclear physics problem issues all understand. I wanted to know which type of nuclear physics may be missing in
For best.
BEST or MiniBooNE.
Yeah. Yeah, I'm most familiar with it in terms of best. Yeah, so there's of course the cross section, perhaps the cross section is miscalculated of the neutrino capture and the gallon. And then there could also be other excited states, which goes into the cross section. Yeah, which would change the expected rate, but yeah, there's one review paper I'm thinking of that I think pretty thoroughly looked into nuclear mismodeling potential solutions, and none of them explain Sage, Galax, and Best.
Same question is the second question is you mentioned the charge current, neutrino argon. Actually, I want to know is there I don't know for theory calculation already can do the description for actually or not.
Yeah, we're using Marlin event generator, which I think is state of the art for the charge current cross section expected in liquid argon, but I think it could be improved.
Thanks, speakers. Yeah.
Thank you.